Hey everybody, in this video we're going to go over characteristics of polynomial and we're going to stick to when you're given the graph for now. So first we're going to talk about how to find the roots and how to find the degree of each polynomial. So polynomial is made up of a bunch of factors and the multiplicity of each root will tell you how many times that factor is going to show up. So when your graph goes through the x-axis very straight, so it looks like that part of the graph is a line, then the multiplicity of that root is 1. So that would just look like 1 of that factor. If the graph looks like a parabola, it looks quadratic, where it's touching the x-axis, but it's not going through, then the multiplicity of that root is 2. And so as a factor, that looks like the factor gets squared. We literally use that factor twice. If the part of the graph that's going through the x-axis is going through kind of curvy, so that part of the graph looks cubic, then the multiplicity of that root is 3. And so in factored form, that factor would have an exponent of 3. We would be using that factor 3 times. All right, now we can't find imaginary roots on a graph. Imaginary means they are not a part of the real number system, so we're not going to be able to graph them. But we can sometimes tell by looking at the graph if there are going to be imaginary roots. So imaginary roots show up when there's a part of the graph that looks like a parabola, but the vertex of the parabola doesn't make it all the way to the x-axis. So it's going towards the x-axis, but it never reaches the x-axis. That's when you have imaginary roots. And imaginary roots come in pairs. You always have 2 imaginary roots at a time. Imaginary roots come from taking the square root. If you remember, the quadratic formula has that plus or minus the square root in it. So that's where the 2 is coming from. 1 is positive, 1 is negative. So if you think you have imaginary roots, there are always 2 of them at a time. All right, so we're going to do this graph together. I obviously drew this by hand, so it's not great. This is actually the first graph that's on the classwork that I'm also attaching for you to do today. So I'm focused on the x-intercepts, and I'm going to tell what the multiplicity is by what the graph looks like on those points. So my first x-intercept, pretend this is -2. Now these numbers might not match your graph in the first example, but this picture is the same as your graph. So see how it's got that parabola shape at -2? So that means the multiplicity is 2. When I'm listing the roots, you can actually list it twice. That counts twice. All right, now I'm going to continue to trace the graph. All right, so that vertex means nothing because it's like up, there's nothing above it. But this vertex does mean something. This vertex could have potentially gone to the x-axis, but it fell short. So I have that parabola shape going towards the x-axis, but not reaching the x-axis. So at this point, there are 2 imaginary roots. There are 2 imaginary roots at this point. All right, so I'm going to continue to trace. And I'm reaching another x-intercept here, and I tried to draw it as straight as I could. But on the classwork, there's like a computer program that they use to make the picture, so it looks a lot better than mine. But see how that looks linear? It's going straight through, and that looks like it's probably 1 on the x-axis. So that root has a multiplicity of 1. That root only counts once. And that I'm putting a 1 here when I'm listing the roots because that point is 1 on the x-axis. All right, then I'm going to continue to trace my graph. Again, this vertex means nothing because this vertex is down and the x-axis is not under it. It was never going towards the x-axis. It's already underneath it. All right, and then again, I tried to draw this as best I could, but it's not going straight through at that point. It's just curving through. So that root has a multiplicity of 3. And it just so happens that that point on the x-axis looks like the number 3 as well. And because it's going through curvy like that, that root counts 3 times. So to find the degree is the sum of the real roots plus the imaginary roots. That's how you find the degree of a polynomial. You add up how many real roots it has and the imaginary roots. So my real roots, we count the multiplicities. So I have this root counts twice, once, 3 times. So that's 1, 2, 3, 4, 5, 6. So I have a total of 6 real roots. Even though there's only 3 different x-intercepts, the multiplicities tell you how many times you count those roots to add up to the degree. All right, plus the 2 imaginary roots that I found. I have to include those 2 imaginary roots that I found. So the degree of this polynomial would be 8. If I knew what the equation was for this, it would be x to the 8th power, x to the 7th. I don't really know what this equation would be without doing the math. I mean, and there could be like plus and minus signs in here, and there could be numbers in front, but the degree is the highest exponent when it's in standard form, so that's how I'd be able to tell. All right, based on the degree, there are certain characteristics that all graphs have. So all even degree polynomials, just like the example from above. If the number in front of the highest x, the LC, that stands for leading coefficient. Leading coefficient. So that's the number in front of whatever term has the highest exponent. If the degree is even, so if that exponent is even and it's positive in front, then it doesn't matter what the middle of the graph looks like, but the arrows will both be pointing up. So both arrows, if I was doing the end behavior, the right arrow and the left arrow are both pointing up. If the leading coefficient is negative, then both of my arrows are pointing down. Again, the middle could be loopy and wavy, it doesn't matter. But if the arrows are both pointing down, I know that polynomial has an even degree, and if it's pointing down, then the leading coefficient was negative. So both of the arrows are pointing down. So you can tell that a graph will have an even degree if the end behaviors are the same. Both arrows are pointing the same direction. All right, odd will obviously look a little bit different. So odd, if it's a positive leading coefficient, the left arrow will be down and the right arrow will be up. So if you connect the arrows, it looks increasing. So the right arrow is up, the left arrow is down. All right, and again, the middle could be doing whatever. This only helps us with what the arrows are doing. All right, and if it's got an odd highest exponent and a negative number out front, the left arrow will be up, and if I connect the arrows, it'll look like it's decreasing. If I go from left to right, the arrows are decreasing. So my right arrow is down, my left arrow is up. So if the arrows are opposite, then you know the degree is odd. So just for an example, if I had this sketch, I can tell by looking at that graph, look at my arrows. My left arrow is down, my right arrow is up. Because those are opposite, I know that my exponent would be odd. And because if I connect my arrows, if I start at the left and I go to the right, because it's increasing, I know my equation will start with a positive. So from this graph, you can't tell what it would be, but I know that it would be positive x, and then I don't know, maybe the 9th power, because that's an odd number, so it could work. And then whatever other x's and exponents would be lower than 9. All right, same thing if you had this one. So again, I might not be able to tell just from this information exactly what is going on in here, but I can tell that both of my arrows are down. So because they're facing the same direction, I know this is even. And because they're pointed down, I know it's going to start with a negative number. So my equation will be negative x, and then whatever even number it comes out to be. All right, so if you need to, watch this video again so you can pause it and take notes. But this should be enough to get you through the classwork for today.